Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will demonstrate Runge Kutta method of numerical differentiation or numerically solve the differential equations. So, before starting this discussion, I will first recall my previous lecture on Euler's method of differentiation, right? And in Euler's method of differentiation, we assumed that the derivative of a function can be evaluated by this stepwise implementation of Taylor series, right? So yi plus 1 was approximately equal to yi plus f of xi yi into xi plus 1 minus xi. So this was actually a first order method. So Euler's method is a first order numerical differentiation method because first order Taylor series was considered. In Runge Kutta method, we have to consider one more term. So it will use second order Taylor series approximation. So yi plus 1 is equal to yi plus derivative of y with respect to x into h plus 1 by 2 square 1 by 2 factorial d square y over dx square into step size square plus so on. So if we consider these first three terms of the Taylor series, then that will be called as Runge and Kutta method. And if we consider first two terms, that will be called as Euler's method. So second order Runge Kutta method is actually based on second order Taylor series approximation, and Euler's method is also called first order Runge Kutta method. So in second order method or Runge Kutta method, the derivative of the function is involved in this expression because we are considering first three terms. So in first two terms there was no derivative term, but in the third term you can see a derivative term, the derivative of this function with respect of function of x and y. So we want to avoid this derivative term because it won't be an numerical differentiation method. If we see a derivative term and if we are required to take the derivative of any term, then that won't be a numerical differentiation algorithm or numerical differentiation method. So we have to eliminate this derivative term from this expression, then that will be a purely numerical differentiation method. So we know that f derivative of xy is equal to partial f over partial x plus partial f over partial y into dy over dx, because this function is a function of x and y is further a function of x, right? So we have to take two derivatives. So first derivative is partial f over partial x and then partial f over partial y, and since y is a further function of x, so dy by dx will also be multiplied over here, and dy over dx is equal to f of xy. We know that dy over dx is equal to f of xy because this is what we obtained the general form, right? So dy over dx is equal to f of xy. So we can replace this dy by dx with f of xy. So partial f over partial x plus partial f over partial y into f of xy. So in order to avoid this differentiation, Runge and Kutta wrote the second order method as yi plus 1 equal to yi plus a1 k1 plus a2 k2h. So this is the general form of this method, and these values of k1 and k2 are described as k1 is equal to f of xi yi and k2 is equal to f of xi plus p1h yi plus q11 k1h. So if we are able to successfully implement this algorithm and evaluate these values of k1 and k2, then this Runge and Kutta method will be a very simple and efficient method for numerical differentiation. So in this lecture, we will extensively solve our complex differential equation using this method, and I hope at the end of this lecture everything will be clear to you. So if we consider this form, we don't need to compute the derivative of this function of x and y, and generally the Taylor series expansion of any function can be written as f of x is equal to f of x naught plus f derivative at x naught into x minus x naught plus f double derivative at x naught divided by 2 factorial into x minus x naught square plus so on. So let's assume that x minus x naught is equal to h, which is the step size. So x will be equal to x naught plus h. So let's put this value in this expression. So f of x naught plus h will be equal to f of x naught plus f derivative at x naught into h plus this expression into h square plus so on. So this is our f of x naught plus h. So looking at this expression, we can evaluate the Taylor series expansion of this K2. K1 is simple. So K1 is just f of xi yi. The function value at points xi and yi is K1. So K1 is a constant which can be evaluated easily, but K2 is a little bit tricky. So looking at this expression, we can evaluate K2. So K2 is equal to this expression x f of xi plus p1h yi plus q11 k1h. So we can write or we can expand K2 first by looking at this expansion, right? So K2 will be equal to f of xi yi. So if we consider this expression, f of x naught plus h is equal to f of x naught, right? Function at this value x naught plus h will be multiplied, and we will evaluate derivative of this function at this point. So f derivative at x naught into h plus 1 by 2 factorial h square and double derivative of this function at this point, f double derivative at x naught divided by 2 factorial into h square. So now apply the same rule for k2. So uh, k2 will be equal to f at xi and yi plus this is p1h, so we will have p1h and derivative of this function with respect to x. So this is our second term, and similarly we can write same expression for this. So that will be q11 k1 h. So q11 k1 h and derivative of this function with respect to y. So this is how we can write k2 by looking at this expression. So this is our k2. Now according to Runge and Kutta method, yi plus 1 should be equal to yi plus a1 k1 plus a2 k2h, and this is yi and this is a1, and k1 is equal to f of xi yi plus a2 into k2. So a2 into this whole expression starting from this point up to this point is equal to this expression, which is k2. So this is our k2 and this is h. Now let's simplify this. So it will be yi plus h times a1 plus a2 into f of xi yi. So a1 plus a2 into f of xi yi plus this h will be multiplied by this h. This a2 will also be multiplied by this h. So it will be a2 p1 h square partial f over partial x. Similarly, this term will be a2 q11 h square q11 h square partial f over partial y, and here we have k1, and k1 is equal to f of xi yi. So this is our whole expression of yi plus 1 according to Runge and Kutta equations. And yi plus 1 in general is equal to yi plus f of x I y I h plus 1 by 2 factorial f derivative of x y at h square. These are the first three terms, and these first three terms were also seen over here, right? So these are the first three terms. Xi plus 1 minus xi is equal to h. So we have written h square over here and h. So let's assume that f yi plus 1 is equal to yi plus f of xi yi into h. This is 1 by 2, and the derivative of f is can be written as partial f over partial x into h square. Similarly, plus 1 by 2 partial f over partial y f of x y h square. So this expression is actually written by looking at this expression, f derivative at x y is equal to partial f over partial x plus partial f over partial y f of x y. So this thing is actually written over here. So this derivative term is replaced by that, and the multiplication is carried out. Now we can compare this equation number 1 and equation number 2, and by comparison we can say that a2 plus a1 is equal to 1, right? We have f of xi yi over here, and h is also here. It means a1 plus a2 is equal to 1. Similarly, this term can be compared with this term, and H square is available, partial f over partial x is present in both equations, and a2 p1 is equal to 1 by 2. Okay, so a2 p1 is equal to 1 by 2. Similarly, this term can be compared with this term, and we will get a2q11 is also equal to 1 by 2. So these things are written over here. A1 plus a2 is equal to 1, a2p1 is equal to 1 by 2, and a2q11 is equal to 1 by 2. So there are three equations and there are four unknowns, right? So we have to make some assumptions. So based on those assumptions, three further methods are actually defined in the literature. So first method is called Hume's method, and according to Hume's method, a1 is equal to 1 by 2, a2 is equal to 1 by 2, p1 is equal to 1, and q11 is also equal to 1, right? So if we apply this combination in these three equations, all these three equations will be satisfied. So that can be one set of solution. And if we consider these values of these constants, then our Runge and Kutta method will be yi plus 1 equal to yi plus 1 by 2 k1 plus 1 by 2 k2 into h. Okay, so we have put all these constants in this equation, and k1 is equal to f of x I yi, and k2 is equal to f of x I plus h yi plus kh, because it was xi plus p1h and it was yi plus k1 q11h. So p1 and q1 both are equal to 1, so this will be our value of k2. Another method is midpoint method. So these set of solutions also satisfy these three equations. So this can also be one solution. A2 is equal to 1, A1 is equal to 0, P1 is equal to 1 by 2, and Q11 is also equal to 1 by 2. If we put these values in these equations, all these three equations will be satisfied. So that can be one more solution, and that is called midpoint method. And the third method is called Ralston method. And if we consider these values of the constants, a2 equal to 2 by 3, a1 equal to 1 by 3, p1 and q11, again these set of solution will satisfy all these three equations, and that can be one form of the solution. So why are we making these assumptions? Because we have no other way, and we have four unknowns and three equations. So we have to make some assumptions, and those assumptions must satisfy all these three equations. As long as this is true, any assumption can be used as the optional solution. So now this is our final form of the Runge and Kutta numerical differentiation method, and we have to solve a differential equation using any of these three methods. Okay, so I have used actually Hume's method, and you can also try midpoint method and Ralston method, and I am sure all those methods will yield the correct solution, provided that you have applied them in the correct way. So I will discuss with you the Hume's method in MATLAB, and then we will see that we will get the accurate solution. So I will be solving this differential equation which I discussed with you in the previous lecture, d theta by dt. This is our f of d theta, and this is our initial condition. And this is a complicated differential equation, and the exact solution of this differential equation is written over here. So this is our original differential equation, and the exact analytical solution of this differential equation is given in this equation, right? So this is the exact solution. Now how this exact solution is evaluated, it is not actually the scope of our today's lecture, because we are dealing with numerical differentiation. But if we know the exact solution, we can do our comparison of numerical differentiation with the exact differentiation or exact solution. So this is our exact solution, and you can see that this is a non-linear equation. So we can plot uh, this exact solution by using non-linear method in MATLAB, and that is carried out by using these steps. Okay, so our time actually varies from 0 to 480, and if we consider this for loop, and this is actually the way of evaluating the solution of non-linear equations, and this is the same equation which I have written over here, and this is the same equation which is shown to you over here in equation 12.13. So you can compare it by yourself, but if we are solving this nonlinear equation in this way, we have to shift the whole equation towards the left hand side. So you can see we have some terms at the right hand side, so they must be shifted to the left hand side, and at the right hand side we must have 0. So we have this term plus this term plus this term, right? So all these terms are written over here, and that's why we have a plus sign over here and a plus sign over here. So these 4 or 5 lines will give us the values of theta for different values of t. So we can plot our theta with respect to t, and t varies from 0 to 480 by following these steps. Now we will solve this equation using the Runge and Kutta numerical differentiation method, and we have considered the step size of 240 in the initial case, right? So for a step size of 240, I have written the MATLAB script. Okay, so this is the same MATLAB script. H is considered as 240 initially. T varies from 0 to 480. This is our A1, this is our A2. And you know that for Hume's method, I have implemented Hume's method over here. And for Hume's method, A1 and A2 both are equal to 1 by 2, and P1 and Q11 are equal to 1. So this is our initial condition. Theta, the first value of theta is equal to 1200, and this is our K1, which is actually f of Ti theta I. Okay, so our f function of T theta is actually the expression on the right hand side. This is our f of T theta. Okay, so this is what I have written over here. This is my f of T theta, and this is K1, and K2 is equal to, let's check from here. So this is our K2, f of xi plus h, f of yi plus K1h for Hume's method. So we don't have any um, t variable in our function for this differential equation. So this f of t theta doesn't contain any t term, only we have theta term. So we will only consider this yi plus k1h. Okay, so because y is our theta, x is our t, and yi plus k1h, so that will be actually our theta plus k1 is again f of xi yi. So k1 is already evaluated in the previous step. Okay, so we have evaluated k1 over here. So this is our k2, and this is actually f of x, f of this is actually our f of xi plus h. X is not present in the function, it will be f of y plus k1h, and k1 is equal to this term. So k1 is already evaluated over here. So this is our function, and we will use theta plus k1, right? Because yi plus k1h. So this is our yi plus k1 multiplied by h, and raised to power 4 minus 81 e raised to power 8. So this is our new value of theta I plus 1. Okay, so after several iterations, we will subsequently evaluate all the values of theta, and then we can plot our theta on top of the exact solution. This is our theta exact, and let's run this code for a step size of 240, and when I run this code, I will get my solution. So this is my solution, and this is exact theta, and this is actually approximate. We have a time range from 0 to 480, and the step size is 240, so we will have only two values. And now let's reduce the step size to 120. Okay, so as long as I reduce the step size, my numerical solution will go closer to the exact solution. So let's run this file again, and here you can see the approximate and exact solution are closing with each other. We can further reduce the step size, okay, to 20. So let's make it 20. and run this file. Now you can see that the exact solution and the numerical solution both are lying on top of each other. So that is all about our today's lecture, and that lecture was very important and technical, okay, because we have compared our exact solution with the numerical solution of differential equations, and by increasing the step size we have observed that the numerical solution actually deviates from the exact solution, and if we decrease the step size, the numerical solution approaches the exact solution. So that is all about our today's lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.